This is supposed to be a tutorial session, so as usual, on the website of the atelier, you can find the slides and you can find a GP code that you can copy-paste in a working GP session, which I encourage you to start now. I will try to print out a number of results, but the main point of this tutorial is to try to solve the cases where the results are actually too large to be printed out. So most of the things would have lots of ellipses and dots, and it's perhaps not as nice as seeing screenfuls of numbers scrolling through. Okay, so what is the motivation? What I'm going to talk about. So here's a very simple sexed field, Q of x mod this polynomial t. Okay, this is irreducible, so this defines a number field. Let's call it k, and the BNF init function basically says initialize everything I might need about this number field, about its arithmetic. In particular, we need to know what its class group and units are. And the first thing I ask about this field is its fundamental units. And 0 here is a sentinel that basically says, OK, it's missing. We don't have them. I hope that's what you have also. Good. Of course, this is a tutorial about handling objects in number fields. I'm not assuming prior knowledge about the Paris functions. If you already know their existing or previous behavior, I try to point out a number of important differences, but please stop me if there are things you don't understand about what I'm computing or what some particular function is doing when I don't think about explaining it. So the second time I'm asking the question, I'm basically initializing with an extra flag. The comma 1 here basically means just insist. I really want this information. I don't allow you to discard the very expensive information. So here I was requesting the units, but without insisting too much. And as a result, we didn't compute them. OK, so this time, it shouldn't take much time, maybe 1 second. And you can see that we have some fundamental units, not too many. I don't remember the signature of this field. I think it's 3 complex places. Not sure. OK, so there are maybe 2, 3. Huh? So yeah, so 3 complex places. So it has actually 2 units. So all those nice digits that you saw on this deleted result are actually just 2 algebraic numbers. Okay, and they are just expressed in the very natural representation as a polynomial lift of these elements in this number field. So it's just just 2 polynomials of degree less than 6 with rational coefficients, fundamental units. Okay, and there's nothing about the representation, initial representation being particularly bad. We had a nice polynomial to start with. It's just inherent. We have some small, in this moderate number field, these objects, the units, are huge. We saw yesterday in Jared's talk that these are an essential ingredient in some constructions. That was Shimura class group in this case. In Orel's talk, the BNR class field, they basically compute units and actually S units and look for generating elements for those Ray class fields that he mentioned as some particular S units that are just, this is just fundamental building block. That's the kind of object that must be incorporated in these constructions. The case of subfields was completely different. There was no units involved. There was no arithmetic involved. It's just field theory. Much, much simpler, small objects. Here, no. OK. So this is problematic because, of course, computing with these huge objects is going to be expensive. We have all the information. They are in exact form. We can compute with polynomials and with rational coefficients. But if they are huge, it will take more time. Second, which is more annoying actually, is that whenever you need to, for some reason, I don't know, units usually want to take logarithmic embeddings and then compute, say, regulators. So you need to understand them as floating point numbers known to some accuracy. And of course, the way the floating point embeddings work is by computing the complex roots of this original polynomial and evaluating this nice polynomial representative at these complex roots. And we get some floating point approximation, but of course, there is a massive amount of cancellation, and we get some result which is usually completely wrong unless we start with a much increased accuracy. Again, possibility of wrong results and certainty of extra costs, because we need to increase the accuracy to make things correct. It's all the more silly because in most cases we don't actually care about this precise thing. In Aurel's case, we wanted in the end some class field. We didn't really care about the units inside. And the way the units are incorporated in computations in Aurel's case was as Selma groups. So we actually work not in K itself, but in K modulo pth power. We have some Kuma theory, pth root of unity, and we don't really need the units, but we need to work with elements which need not be units in K this time, but with modulo 6 powers, or pth power, sorry, not 6, 6 is not prime, are actual units. So we have a huge object, but which we might not need. And sometimes we need just some non-Archimedean information, some image in some residue field, or just, as above, an approximation to floating point embeddings. And we don't really need that huge object. And finally, just computing a very simple algebraic object may just overflow the possibility of the implementation. If you try this in GP, you will get something like overflow in LG or in Expo or in whatever. It basically says, okay, this very simple formula with very few characters cannot be actually represented as an expanded integer written in binary. Okay. Good. So that's the motivation. So we don't want huge objects in algebraic number theory, even though they exist. Okay, so just some general notations, and then we come back to our problem. So, in general, we're given a polynomial, irreducible over Q, which defines some number field of degree n. It has a signature. We have R1 real places, R2 complex places. S infinity is the set of Archimedean places. Its ring of integer zk is a free Z module of rank n, whose basis we call B1, Bn. All this can be accessed with a Paré function, but I'm not explaining this at this point. It's just the setting, the setup. It has an absolute discriminant, which is the discriminant of this lattice zk with respect to the trace pairing. It has an ideal class group. It has units. Now this is something that we want to talk about. This unit is a cyclic torsion part. So W is the number of roots of unity, Wurzel, I guess. And then it has exactly R1 plus R2 minus 1 independent generators of infinite order. Then for any set of finite places, we can generalize this and define. So these are the units in the talk. These are the S units in the talk. And we're interested in that because lots of natural algebraic number construction start by fix a set of bad places, and then we consider only S units. And because of this finite S result, we can actually prove that this is also a Z-module of finite type, which basically has exactly the same torsion part, a few more independent generator of infinite order. The total number is the cardinality of S, which here is, I assume, contains the infinite places. So that, of course, when S0 is empty, this is just R1 plus R2 minus 1. And the total number of generators, finite order or infinite order, is just the cardinality of S. So a small finite number. And these are, I want, for instance, to be able to compute. So these were the fundamental units. The FU in the previous slides were just U1 up to R1 plus R2 minus 1. So in this case, just U1 and U2, because we had R1 0, R2 equals 3. So dot FU, that's what it means. I want to recover just these algebraic numbers. OK. So this is math. In Paris speak, we basically have two constructions to deal with general number fields. The first one is the simple arithmetic, which is called NF init, number field init. You give it as input a polynomial t, and from that, you can compute all kinds of things. So defining polynomial, that's just t. Sign, that's just the signature, the pair R1, R2. You can actually ask for R1 or R2 separately. I didn't write it up because we don't have enough space in this line. Zk is actually the Z basis. Discriminant is dk. K dot p I discovered while preparing this tutorial. I completely forgot and I had introduced that. But it's all the bad primes, so it's the list of ramified primes. So it's the prime divisors of dk. It's available for some reason. I just checked what was the list of member functions. That's the dot notation is the member function notation. Bill mentioned the user member function. These are the built-in member function, and I discovered that this built-in .p method also accepted elements in the NF init class. Okay, so you have the list. When you ask question mark dot, you get the list of all the available global methods and the classes they apply to. So whenever you have an NF in the column, it means that it allows to retrieve something useful in some NF init structure. Okay, so basic initialization having to do with the field theory and the ring of integers, no more. BNF init, so this is historical names, and we'll see later that maybe it would be much better to handle this the way we handle elliptic curves. The way we handle elliptic curves is we just initialize, there is a function L in it, we just give a model and basically don't compute anything. And then we have some partially initialized object, and whenever we need to actually compute something, we just compute it and then store it in the structure. Here it's completely different, but we are somehow evolving to that model. Maybe next year we will have a tutorial explaining that NF init does nothing except store the polynomial t, and anytime we access something, it's computed and added to a structure. Maybe it will evolve this way. Not now, yet. So now we have two completely different functions. The second one, which is conceptually a superset of the first one, the BNF init from the first slide, actually asks for the more complicated arithmetic invariant. In particular, the class group, CLGP, the torsion unit, which is not very complicated but belongs together with the units, so W and zeta W, and the fundamental units. Okay, so whenever you have a K, as in the previous slide, which is initialized with NF init only, then only the methods in the first line, the simple ones, will be available. Whenever you include the B here, some big NF init, or actually NF init completed with Buchmann's algorithm. B is for Buchmann, not for big, but that's maybe easier to remember. Then further methods are actually available. So whenever you initialize something with BNF init, the simple invariants are available together with second one. So actually, a BNF init of T does contain exactly an NF init of T. It's just more complicated, more costly to compute. So by default, we assume that that's not what the user wants. So the initialization function does not compute anything to do with units and class groups in NF init. OK, so that's the math and the corresponding structures. So now, how do we represent elements in these number fields? So you notice very quickly that most of the functions in Paris have a prefix. Here are a number of examples. I'm not yet explaining what these do. Whenever a function starts with NF, you can expect that it will need to take an argument, which is an NF structure initialized by NF init. Whenever the name is the prefix starts by BNF, you can expect that it takes as argument a BNF, a big number field, as initialized by a BNF structure. Right now, I'm handling just elements in the field. OK, so they can be given as rational numbers or integers, just as you would input them normally. So 2 or 1/3 are actually members of all the number fields. They will be recognized as elements, as arbitrary number fields. They belong to the prime field, so OK. Remember, a number field K is just given by a model Q of X mod T for some fixed T. So you can actually write this with a Paul mod. So this is 1 plus X bar, where X bar is a root of T, the canonical root of T in Q of X mod T of X. Actually, when we do expect number field elements, we accept the lifted form. So it's clearer to use the Paul mod notation, but 1 plus X will work just as well. As long as we know that we are in a number field function, NF whatever, which will take an NF argument somewhere which contains T. Now, of course, these guys don't belong to every number field. Of course. And when you want to do some natural mathematic tricks like a field extension, you have something mod T, you have something mod, say, R, some other polynomial corresponding to some primitive element in a field extension. You cannot compute simultaneously mod T and mod R, because you just have two irreducible polynomials, and the only ring in which you can project these elements is just the null ring. Right? Mathematically, you want to do an extension, but as Paul mods, you're working in a null ring, which is not what you want to do. So this is really for a fixed number field. You cannot really do extensions in a simple way with this notation. And now we have a slightly nicer notation, which usually reduces the size of the objects involved, because we know that Zk, the ring of integers, has some basis which was fixed and computed by NF init. So the Wi here should be some Bi's. There were the Bi's here. Sorry for the typo. And we just represent integers, algebraic integers in Zk, as an integer linear combination of the Bi's, just by the vector of coordinates. And of course, by extension of scalars, we can take Q linear combination. They are just elements of K, because K is the field of fractions of Zk. So when you just have a column vector, the tilde here is important. It's really a column. We're doing linear algebra, and there's a very unfortunate but very important distinction in Paris between horizontal and vertical vectors. Vertical vectors are elements in vector spaces. Horizontal vectors are, I don't know, collection of elements, which is something completely different. Yeah?
So tilde is lacking the nth element add example?
Yeah, I forgot the tilde. This is, as I said, this is just a collection of 3 numbers. It has nothing to do with an algebraic integer. So this one will not work. If you add the tilde, then it will work. I was going to explain this. So, okay, so this is how we represent these elements. And by default, the functions handling algebraic numbers will try to return elements in this form. This is the preferred form because the basis for the ring of integer has been somehow minimized. Some optimization have been performed on the chosen basis. We don't pick some random basis. Even if the initial polynomial t is completely random with huge coefficient, very badly skewed with respect to the number field you're computing, the integer basis we compute is actually small in some well-defined sense that can be expressed only in terms of the discriminant of the field, in terms of really, so the input we have, the polynomial t, to define everything, is highly non-canonical. Many polynomials define the same number field. And so this is a highly non-canonical way of working. Okay, it's canonical in the sense that you fix t. So you know what you're doing. But just in case you didn't know what you were doing, and maybe you chose the wrong polynomial, this representation makes sure that elements which are small with respect to canonical theoretical measures, like the size of complex embeddings, for instance, height, something which has small height, something which is intrinsic, will have, by properties of our computation, a small representation here. Whereas here, I mean, even algebraic integers can have denominators, huge denominators, and you have little control. So this is the preferred representation. And of course, elements in the prime field are easier to express as integer or rational numbers. Okay, so here we are initializing some much simpler number field. We're multiplying 2 elements. So implicitly mod x cubed minus 2. So just think of x as being cube root of 2. The algebraic cube root of 2. Of course, there are 3 cube roots of 2. We could multiply by a 3rd root of unity. But here we are really computing in k of x mod x cubed minus 2, and there is a canonical cube root of 2 in there, which is x bar. So I'm not talking about this kind of things. This is really not as an embedded field, but as an up to isomorphism, a canonical algebraic structure. So here we're computing the absolute trace of an element. Here we're trying to add 2 elements, but we forgot the tilde, so we get an error message. And of course, if you add back the tilde, you know, you see there's room here for the tilde. you see the space. You could have guessed that. Then we actually, so this shows that the function that just adds 2 algebraic numbers doesn't really care about what the representations are. You can mix the formats if it's more convenient for you, as long as you use them properly. Here we're just going back from one representation to another. So this is the basis form. This is the algebraic form. And so alg to basis puts some object in basis form. Basis to alg puts the object in the algebraic form as a Paul mod. And percent is just the result of the previous computation. So of course, this is an involution. I mean, this is a idempotent. Sorry, when you just iterate it over the same element, once it has the required representation, it stays the same, and these two are inverse of each other. These are obviously bijections. No problem up to here. So this is traditional Paris way of initializing number fields and working with their elements. I will talk very little about ideals in this talk, but later. My main problem is big elements in particular units, which are very often huge, and then you can do nothing about it intrinsically. It's not a problem of any of these representations for the fundamental units will be huge. You can try with a previous K, not this one has small units. The previous one, we tried .fu, and we had some huge Paul mod, but you can try alg to basis. It's not going to be much nicer. So in all these representations, the objects, like fundamental units, will remain huge. Okay, just for the record, I'm mentioning quickly, because they exist, other representations of algebraic numbers, which are all lossy. They all lose some information. So here there are no tutorial, no examples. I'm not explaining how to use them. Just mention they exist and the name of the function in case you would like to check the documentation. So for instance, you can use some kind of Chinese remaindering techniques. Instead of handling elements in K, maybe you just want to know that some congruences hold, and maybe some sign condition or some Archimedean size condition. And if you add, of course, enough condition, you have a single element, but that's too many usually, infinitely many. Here, just like working in Z mod NZ, if you know that you want to represent integers between 0 and n, okay, you lose no information. But for arbitrary integers, you do. And the function ideal Chinese allows you to recover from local information one global object satisfying all the constraints. In principle, there will be infinitely many meeting the same constraints. So we lose information if we use this. Of course, representing elements by list of congruences, we completely solve the problem of having a coefficient explosion. But we lose information. We can just, okay, this is a direct case. We just work in the residue field. Okay, it's finite, small. We can work with complex embeddings. Then here the point is that we actually have complex numbers as floating point numbers cut to some accuracy. And there are infinitely many algebraic numbers compatible with the information we have. Just like when you work with rational approximation to some real numbers. You lose a lot. Lots of numbers disappear this way. Okay, you can have projections to more general finite rings. So like this ingredient, this is one ingredient of the Ray class groups that were mentioned yesterday. And the ideal log function is one way of representing elements in this Ray class group. We can actually work in K star modulo powers, just like we might need for the Biana class fields. We can also, in a different direction, factorize into prime ideals, consider the elements as principal ideals. So basically, we're computing modulo units. And of course, this would kill all the huge units that we saw before, because the units just generate the full ring of integers. But that solves the, in some way, maybe not the right way, but in some way, the fact that units are huge, they are killed by this construction. And here we're doing even, so ideal factor is just another way of organizing this information. We could just use ideal HNF, which represents an element by the principal ideals that it represents. Okay. So they all are useful in different contexts, but not really in the context of we are having some huge element representing some information. We want to keep all of that. So none of this, all these are lossy representation. We lose information. No good. Okay, so what's new? What's new? It's a completely stupid idea. It's basically the idea of factoring things without factoring things. So this applies to multiplicative contexts only because this is how it's implemented. It could be done in more general contexts, but the context I'm mostly interested in here is units and S units. So it's really multiplicative groups. And the idea is that naturally those objects occur in multiplicative forms, in expressions of the form product of the GI to the EIs, where the EIs are just exponents, some integers, positive or negative. The GIs in this case are just algebraic numbers, elements in K star. And what we are really considering is such a product. And it turns out that this is really the way we compute objects. The units in a number field, they are really represented as a product. They are computed internally as a product of S units, which are accumulated during the BNF-init algorithm with exponents that basically arise from linear algebra. We do some linear algebra on the exponent vectors, and we get exponents. And what can happen, what does happen actually in BNF-init, is that those exponents are huge, like 2 to the 2 to the 100. This is actually a small exponent. That's something that you cannot expand and represent in Paris, but that's a relatively small exponent arising in the computation. So the idea is completely stupid. It's just, okay, this is a factorization. Treat it as a factorization. Factorization matrix is a two-column matrix. First column contains the GI. Second column contains the EI. Okay, so this is an internal representation without really any mathematical content. Of course, we don't turn anything into a UFD. We don't have unique factorization at all. The GI need not be coprime in any way. In particular, testing for triviality or equality is very hard. Just representing objects and doing multiplicative operations. Because, of course, just like Bill explained about the math-reduced function, the right way of computing the factorization of a product of two objects when you already know the factorization is actually just concatenating the factorization. It's certainly not to expand everything and factor from scratch. So multiplying such objects is trivial. Adding such objects is highly non-trivial, and we won't do that, never. Because you never add units. Okay, you can be interested in exceptional units, solve u plus u prime equal 1, but this is a very hard problem. I'm only solving trivial problems in a trivial way. Hard problems are difficult. That's one thing that's bad about them. Okay, so the goal is just twofold. We just want to avoid coefficient explosion, where the coefficient explosion is just measured in terms of the actual size of the internal representation. So if we compare this is a factorization, 2 to the 1,000 times 3 to the minus 2,000. Okay, you can just check what it gives in GP. It's not very informative. I find this formula, even if I had not known that 2 and 3 were coprime, I would still have preferred that representation to the one that we get by expanding it. There's much more information there. And the second goal is whenever we have, we're in multiplicative context, meaning that we have a morphism from the multiplicative group of K to some abelian group G, then we're in business. We basically apply the morphism to each of the GI, leave the EI in place, and go on. So we can very easily, in a trivial way, compute such morphism, keeping this factored representation. So in order not to use the word factorization, which somehow to me implies a unique factorization, this is what we call compact representation. Don't think of topology, think of, we concentrated sparse representation if you want, but okay. Okay, and the name existed already in the theory, because already in Buchmann's algorithm, the compact representation of units was mentioned, and this is what was implied. Okay, so this is the concept. Not very hard. There are drawbacks. There are drawbacks. First, multiplicative operations become trivial, but non-multiplicative operations sometimes become much harder. For instance, just checking whether something is 1. It's very, very hard to check whether something is 1. In fact, when you think about it, some of the properties of the operation change a little bit. We lose some of the properties, like checking whether something is 1 in an expanded representation as a polynomial is easy. You check whether all the coefficients of all the monomials are 0 except the constant coefficient. And checking whether it's not 1 is equally easy. You check whether what I just said is not true. But here, when you have something that is not 1, it's actually trivial to prove it, because you just map it to some group, any group you like, a nice one, small one in which you know how to compute, and check whether it's 1 or not there. As long as your mapping is not too degenerate, and you should know what you're doing since you created the object, it shouldn't be too hard to concoct some group in which this element, which is actually not 1, remains not 1 in the group. So you have a very efficient probabilistic test to check for non-equality. But if we fail to prove inequality, it doesn't mean that we proved equality. So checking whether something is 1 becomes easy in some cases when it's not 1, and very hard in the other cases when it's 1. So theoretically, things become a little more messy, and we might need to replace deterministic algorithms by randomized algorithms. Second, whenever you have a non-generic simplification, so non-generic just means that for some reason, I don't know, 6 and 4 are not coprime, and when I have some factorization involving as generators 6 and 4, some magic might occur and some simplification, some cancellation might occur. What happens when I have x to some power times x, the same x, to some other power, then I can merge things, just like the mat reduce function does. In particular, when you reach x to the power 0, you can remove x from your generators. So anything that's formal like this is very easy to take into account. Anything that's not formal, that's not generic, that just depends on some arithmetic condition, which I don't really know how to check. I mean, of course I know, but not directly from this representation, is not taken into account. So when the actual result is small, it happens in many cases that the units of your number field are actually small. This compact representation might turn out to be much larger, because when you write it as a factorization, you have lots of generators, huge exponents, and for some reason they all cancel out, and when you expand everything, you get 1 plus x. It can happen. There are lots of nice examples. So this doesn't mean that it's optimal with respect to size. It just prevents the generic explosion that you could expect from the algorithm. It doesn't profit from the part that sometimes this explosion doesn't actually occur and you have simplification. So sometimes you get larger objects. Not huge objects, but larger than some other representation, the naive ones we saw. And the main problem, yeah?
At the same time, you might be likely to not be able to compute the small operation, because if you do x to the power 1 million and then you do y to the power 1 million, they cancel out. You might not be able to go beyond the intermediate explosion. So it will still be useful to have this.
Yeah, I mean, I'm just saying this is not a universal solution to all the problems in algebraic number theory. I'm not saying that we're not going to use it. Actually, we're going to use it in every single algorithm internally, almost, in multiplicative context. That's what I'm going to report on. But what happens very often is that you use some kind of symbolic numeric technique where at some point when things start to blow up, you just replace by complex approximation. And in the end, if the object is actually small, you can actually recognize it algebraically from what you have. That's the way we were working before. It's not guaranteed to work, but it works in many cases. So the main problem is the last one. The main problem is the last one. I just told you that all the functions in Paris which handle elements were expected to return, in most cases, column vectors expressing things in terms of the integer basis. So we cannot really change all the existing functions or many existing functions to just change the representation, because we noticed that there's a better representation, and any user that were expecting a result in a certain form will get it in a mathematically equivalent form, but a computer sense, computational sense, it's a very different type, it's a very different object, and anytime you do some kind of hard-coded, unstructured programming, not thinking about elements in number fields, but about, I really want a Paul mod here, and I'm using ALG2 basis, then the program breaks. So it's very easy for us to change everything, but it breaks. It has a very good chance of breaking lots of programs. We tried it on a few sample programs. Every single one broke. Not ours. Yeah.
When you fail to prove equality,
yeah.
When you fail to disprove equality,
inequality.
You can do a Chinese reminder theorem and prove equality.
It depends if you need bounds on the size of the object.
Yes.
And the bounds you get are usually in the construction. You include generators to the power 2 to the power 100. This is a small object. The bound you get from this, you really, the Archimedean bounds you get are absolutely horrible. What does save you is that some non-generic simplification occurs, and somehow things cancel out.
But could you compute the log embeddings from this and then prove that the size is actually small, and then
how can I do that? I cannot even prove it's an algebraic integer.
Well, okay, GIs, they're not smooth.
No,
Okay.
I'm not assuming anything. There are many cases where you cannot do things.
Yeah.
It's a problem. It makes things a bit more complicated. But the main problem is the last one. So I'm going to explain the solution we found that basically makes sure that all the previous programs still work, maybe not in the most optimal way, but you can use the new way and profit from the fact that, in fact, those objects can be represented in a better way.
Try to not to use equality.
It's different. I'm going to explain. Things. OK. So here's how it works. Well, this is some implementation report. So first, of course, high-level function. They transparently, if some function creates a structure internally and handles its elements, it's going to use the efficient representation. So the BNR class field, the BNF init. So BNR class field needs to compute a BNF init internally. So it does that and handles elements as compact representations. Solving two equation does compute a BNF init. It uses compact representation, and so on and so forth. So whenever our library function needs to create a number field structure, they do right away what's necessary. In GP, you can't do that. It's not a high-level programming language yet. And OK, so what's the actual strategy? Remember the comma 1. So comma 1 used to mean, I really want the fundamental unit. Make sure you give me, eventually, in algebraic form, the fundamental unit. But in many cases, you don't need actually that. For instance, just the floating point embeddings of the units to some precision will be enough. That's not enough to reconstruct the units, because they are too large. But in some cases, like you just want to estimate the regulator, that's enough. You want to estimate the regulator to some precision, so just some floating point data is enough. So by default, and it's the previous algorithm, we're happy to work with some lossy representation, representing algebraic numbers as floating point numbers to some accuracy. and see where it leads us. In some cases, in many cases actually, it goes all the way to the end, and that's what it used to do. It can fail for some applications, because in the end you end up with floating point data, and that might not be enough to reconstruct the object you're actually interested in. So, for instance, k.foo in the first slide gave 0, because it was enough to estimate the regulator, it was enough to compute the class group, it was enough to solve the discrete log problems. You can actually solve discrete log problems in the unit group. There exist some units which are uniquely defined by the information you have, except that with the information you actually have, you cannot write them down. It's enough to solve many problems, but maybe not all problems. So that's why sometimes you get 0 or some errors like missing units in BNF. Please compute with comma 1. Okay. Second way, comma 1. Basically, so it used to be something like increased precision until everything is fine, and we get some algebraic form for everything. Now it means exactly the same thing functionally. It means compute everything in algebraic form, but not by just by increasing the accuracy until everything works, by using what I explained behind the scenes. So it means that this BNF with this comma 1 now contains algebraically all the data that will be needed in all the functions later. So any function that takes as a BNF and that might need some data that could be present in BNF will have this data in algebraic form. That's the contract. That's what comma 1 means. So it has some drawback. It uses more memory, definitely. So the BNF init function itself will use more memory, maybe 10 times as much, not much more. Sometimes it's just the same, but when you add this, you anticipate that you will need more memory. Second, it can be slower in the worst case. So sometimes we have benches where a given BNF init computation is twice slower, 3 times slower, 5 times slower, very, very rarely. But on average, we had a huge list of benches. When we just sum out over all the fields, the slowdown was not noticeable. So BNF init, in principle, when you add this field, will use more memory and can be slower, but not much slower. So what we advise, the new strategy is just add this flag, always. If it causes this particular function to run into a problem, remove it. Of course, the upshot is that once this initialization finishes, all the other functions will have access to that data. So by solving this initial problem of computing everything algebraically, you solve all the later problems that some function might not have available the data it actually needs. So if the initialization works, everything else is going to be much faster, simpler, and will prevent the slightly problematic case. In some cases, this original initialization will fail. That's possible, because it will use too much memory, or maybe there are some examples where there is a 100 times slowdown, which we haven't found. We can't rule it out. In practice, we don't see it so far. Okay, so just use this.
If you do a benefit principal later, then you will have the same problem.
I'm saying that if you're using BNF init only to compute the class number or the class group structure, you don't care at all about the units. So you don't need this flag, ever. If you use it as an initialization function to do something else having to do with units, class group, and so on, and not just some raw data, then okay, you're much better off. But if you just want to do a table and check class numbers, okay, you get a slowdown and no benefit, which is not quite true, actually. It might happen that this is much faster than this, because in tough cases, this is much faster than this, without the flag. For the simple reason that some huge objects need to be introduced, and in the symbolic numeric algorithm that I described, handling floating point numbers, for some reason something is wrong, we don't get, we lose all accuracy, and we have to start over at a higher accuracy. In this algorithm, we don't start over. We have all the information always. Yeah.
Is it also possible to get a correct result with the second one and the wrong one with the first one? If something floating point goes wrong?
Not in our current experiments, but it's definitely possible. It occurred. Yeah. It's actually possible to get a wrong result in the second case also, because some functions are not entirely certified. We don't use ball arithmetic throughout. None of the floating point computation in Paris, whatever the function, is certified in any sense. We do our best. We use some algorithm, but we don't use basically the algorithms that will allow us to prove that every single floating point number we get is actually within guaranteed rational bounds. That's something that can be done. That's done in ARP, for instance. That's done in yeah, I mean, and it exists for some subset of things we do. But in principle, there's always the risk that something will get a wrong result because some floating point number somewhere is not entirely correct to the accuracy we expected. It has certainly occurred already. This is a general problem in Paris, not this function. Okay, now back to tutorial form. There's no problem with the concept. So one thing to remember, whenever you have a BNF init in your computation, in your scripts, and you do it to initialize something, do some later work, and not only to compute a class number, add a comma 1. This doesn't change the BNF init structure in a functionally noticeable way. You get the same results, or better. So what happens now? Now we have a problem of compatibility. BNF.foo was meant to return the fundamental units in expanded form as Paul mod modulo t, the polynomial. We cannot change that. Even though they are represented in a different way, if somebody used this method to recover the units in a given form, we cannot give the factored representation instead, because that's not backward compatible. So this function still does the same thing. It still returns the units in expanded form, which may be very, very, very expensive. We actually have a very complicated implementation to make that less expensive. It uses multi-modular computations and lots of things that come from actually the early NSF algorithms and computing square root in number fields. We basically have some result which should be, in the end, small, which we hope to be small, and we get as much information as we can about it without computing it directly, trying to reduce the cost. So this is a very complicated algorithm. It used to be a simple accessor. It says, we computed the units from BNF. They are either stored in there and we get that instantaneously, or they are not stored in them and we get 0. Now we can take infinite time just asking for it. But in the cases where it returns something else than 0, it will return the same result. Okay? So this is something you don't want to use anymore, because this can be a very costly operation whose only purpose is to take some object that we know in a good representation and transform it into a very bad backward compatible one. So if you have it, it will still work, but don't use it and don't expect it to be free. The result is actually cached. So if you do it once, and it takes some time, if you do it the second time, it will be instantaneous. So we have some example here. So this is the first caveat. Beware of BNF.foo. The second one is the BNF is principal function that actually computes a discrete log in the class group. So you start from an ideal, I, and you're going to, so you know that the class group of K is actually isomorphic to some product of cyclic groups, say in SNF representation, And you know some generators. So the AIs here are some ideal that form independent generators of the class group in this precise sense. So any ideal can be written as the principal ideal times. So these are just these same ideals to some power, I don't know. So this is what I call solving the discrete log problem in the class group. There are some exponents in terms of the generator, and there is a principal ideal here. When you ask for BNF's principal, it gives you the Ni, I think. Or maybe the Ni and alpha by default. So by default, the Ni and alpha, and you have a flag to say, I don't want alpha, I only want the Ni. Okay. And of course, alpha here has the same problem as units before. It's usually a huge element. So here is some very simple example. So this time the field is quadratic, real, small discriminant. I mean, there's nothing particular about this one. This is typical behavior, like 10 to the 7 or something. Prime, maybe. Don't forget the comma 1. And this time, you can ask for the fundamental units as before. Takes a lot of space. You can ask for the units. So this is a new function, BNF units, that, yeah, I forgot to mention, it's on the slide. It's the proper modern equivalent to BNF.few. It basically gives the same output, but in factored form. So you get some factorization, and if you look at the factorization, you can see that this is a very simple example. You can see that the exponents are a bit large already. I think they are, there's a 2 to the to some minus 20,000 or something. I mean, for a very moderate object that's almost instantaneous to compute, you get a factorization which is highly non-trivial already, but still tolerable. And you can compare with the expanded form. And now I'm going to pick a prime ideal above 2, so very, very small norm. So this is actually the first. So 2 is actually, well, split here. So this is a ideal prime deck would return a list of 2 maximal ideals. I'm taking the first one. This is called P. And I'm asking to compute the discrete log. So you can ask what is k.clgp, what is the class group. I think it's trivial. Don't quite remember, but when the class group is trivial, all these ideals are just, I mean, they're not there, they're just zk. So we just want a principal generator of I. And if we just ask with an existing function, is it principal? We get the answer, yes, it is principal, and a huge generator in expanded form. You don't? Oh, even worse than that. Okay. So this is the case when you try to do without factorization, without the compact representation, and it fails. This is a bit silly because we do have all the information we need, but the old algorithm is not able from floating point approximation to reconstruct the result. So if you do it at a larger precision, that was what you would have been inclined to do, I hope, then eventually it will work, but it's going to be complicated, messy, whatever. Now there's a new flag for BNF is principal. So we've seen that BNF.foo is deprecated. You should use BNF units to get expanded representation. BNF is principal. The default form is deprecated. You should use the new. So the flag is actually a bit flag. There are many properties. One bit is there to say, I don't want to see the generator. 1 bit is there because it was there before and it serves no purpose, but we cannot remove it because it existed. So this is the first available bit. And it basically means I want the correct, what should be the correct proper default behavior if backward compatibility was not a problem. And it means I want the exponents and I want the alpha in factored in compact form. So with the same field, with the same data, here you will get a result. Here you get a failure, you get a failure like, okay, precision too low. Yeah.
I don't quite get the result of BNF units. There should be 1 unit, but I get a vector of 5 components.
Yeah.
So what do I do with it?
This was a white lie. The first component is the units. The rest is technical data, which I'm going to mention in the next slide. So the exact equivalent of BNF.foo, I mean, to get the exact mathematical information, is BNF units of BNF bracket 1. We only want, if you only want the units, it's just the first component. But in fact, it's a structure that represents the units as a whole and allows to solve discrete log problems with the units. And we'll see in the next slide that the same function allows to handle S units. There's nothing specific about units. They just correspond to the S0 set, the finite set of non-Archimedean places being empty. But if you want S units, it will be the same function, the same construction. And then the other components will be useful.
The first component is still a two-component vector.
Because we have 2 units, I think. No, no, we don't. Ah, sorry. They are all the units. And there's a torsion unit. There should.
Okay.
So it's yet another white lie. It's not exactly the same as foo. So if you want an exact equivalent, it's 2 foo. It's foo2. It's foo2 in old Paris speak. So it means everything is lost in French. Or something like this. No, okay. Okay. We're in slight trouble because the previous situation was not completely satisfactory. What is meaningful is U of k, all the units. Usually you're given a unit. And even though you know it has a torsion part, it's a cyclic part, and a free part, you're given a unit and you basically, so you remember there was this z mod wz times z plus, then we have some z to the r1 plus r2 minus 1. Okay, just isomorphic. And cleverly, the old Paris functions solving discrete log in this group would return a vector with this particular exponent. So it would mix int mods and integers. And then, of course, everybody would start by removing the int mods, lifting everything to z and do things. Right. And then you had dot tu to get something about the torsion part, dot fu to have the infinite order part, and some historically deprecated deleted function called foo2 and 2foo. Both mean something in French. And which basically say, okay, I want first the fundamental units, then the torsion units, or the other way around. Okay, not anymore. And this is, so this was just meant to see that you can compute some objects. The way they are used is explained in the next slide. But what you should think about is that you usually don't want the units themselves. You want to solve discrete log in this group and express arbitrary units in terms of these units. So of course you want these units, but you want to do more with that. And second thing, it's usually not units, but S units. And this is something we're going to see next. So here what I wanted to show in this slide is just that older functions and some close modern equivalents have different behavior and give different results. Here, for BNF's principle, there's no problem. You really get a vector of two elements. One gives you alpha and the other gives you the exponents. That didn't change. The one thing that changed with the flag comma 4 here is that this alpha is now expressed in compact representation. That's all. And before, it was a polynomial? I don't know. Maybe it was expressed in the terms of the integer basis. In basis form. That's better. OK. So this is what's changed. And of course, we had an old flag, existing one, to BNF's principal, which basically meant I do want the alpha part, the principal part, in case of trouble, increase accuracy and start again. Don't do that anymore. We have a good solution to this. Comma 1 first. And once you have this comma 1 here in BNF init, you have everything in algebraic form. And the algorithm is guaranteed to succeed, provided you ask for the result in this form. The reason why it didn't work here is that I didn't want to implement in that particular case the expansion. Because without the flag, we know how to compute the factored representation, but we need to expand it because without a flag, we must return it in expanded form. I did that for the units because units are much, much easier. They are not divisible by any maximal ideal. That helps a lot. And here is just previous algorithm was unable to do it. I'm still unable to do it, even though in principle I could do it. The right way to do it is to insert this flag as default. This is a bit silly because in principle we want the default flag, the default situation to be the most useful to the user. But in this case, what we decide is that what is most useful to user is backward compatibility. That's just a general decision we make. It's better to be consistent rather than just change it because this time it's really, 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 really useful. So remember, comma 1, comma 4. These are just the two functions where you need to. Yeah, perfect. This is the. OK. Addendum. So actually, I'm not interested in units, but just S units. And the same function that computes units, there was no argument before. It was just BNF units. Now it's BNF units, and you add an S, which is optional. S is just the list of prime ideals above 2. The 2, we just want the 2 units. And we get a structure which represents the S unit group. The first component of that structure is the list of S units, the full generators. There's no two full uniformizer madness. You have cardinality of S elements, because that's the number of generators. You get them all. And they all have the same status. OK, some of them have, one of them actually has finite order. But it doesn't matter. What happens is that it's there, it's in the list. I think it's guaranteed to be first or last. I don't remember. It's in the documentation. If you really need to know which one is the one which has infinite order, it's always at the same place. Previously, what happened was that we were working in Foo2P representation, meaning that first units were fundamental units, then we have the torsion units somewhere in the middle, then we have uniformizers coming from the prime. And then you get some vectors with some int mod in the middle. And of course, anytime you try to do linear algebra with it, everything fails. So now everything works in a, I don't know, more high-level way. You have this U group that allows you to ask whether something, OK, is a unit here? I'm not using U. Is 2 a unit? The answer is no. And if I want to express 2, which I know is a 2 unit, essentially by definition, in terms of the generators that are stored in U, in terms of the ones that are implicit in this representation, I can get it just by adding this U argument to BNF is unit. So there used to be a BNF is S unit function, which is deprecated. Now BNF unit computes the unit group or S unit group. BNF is unit computes the discrete log in this group. There's the mode, okay. And now something that changed, there's no mode anymore. It's really the exponents, even though one of them is modulo the order of the torsion unit. You get the actual exponent. Okay?
Yeah, so if I don't want S unit, but units,
you don't use the S argument.
Does it make a difference if I use the unit bit, if I compute the U or if I don't?
Makes no difference. So if you, in fact, in U itself, it's just a device, in this case, to access the fundamental units themselves in expanded form, because there was no function in Paris that allowed you to access that. But if you only want units and you don't want to do, you can just do everything. You can do BNF is unit like this without using the U, without using BNF units, except that you cannot know without BNF.foo or other deprecated constructs with respect to precisely which unit you're computing. But abstractly, in this group, as a black box, you can, yeah, sure. So the extra S argument is just meant as an addendum. If you need S units, you can get them. With the same function, just add some extra argument. That's all. Okay. So now just some, I'm almost done. Just some example that show you that if you have an element in compact representation, because you picked it from BNF units, for instance, or because you built it yourself. Here I'm building 2 elements by hand, because I want to build them in this way. Most of the time, it will not be done in this way. You will just use the actual components of BNF units and get the fundamental unit in factored form. And what happens is now that all the old functions handling element in number fields, as long as we are still in multiplicative context, this is important, this is an important restriction, they will be able to handle factorization matrices as well. So one thing you might want to do is, okay, you don't want to do that, but just in order to check that things are still correct, you can factor back things and get the expanded representation. Of course, this defeats the whole purpose of using compact representation in factorization forms, but sometimes it's good to see an actual number field element. So U in this form is actually this in basis representation. So this existed before. This was actually one of the only function that was explicitly meant to handle factorization, but to get rid of them. We don't want to do that, but it's still there. If you multiply 2 elements, well, you get the concatenation of so U and V. You can work out. So it's not very useful in the sense that we could just have concatenated the matrices, but the function does it, so it's fine. So this is basically meant to show that everything that should be expected to work, well, hopefully works. Yeah? Yeah, but that's because I forgot. This an output. You're not meant.
The same element appears twice for the
Yeah. Yeah. It doesn't take into account, so you can change that a little bit. Just add, I don't know, here, x to the power 3. Here you should get a 5. So there is no non-generic simplification, but we're really working in the free abelian group Z of K star, and we have unicity in that group.
So infinitesimal does this not reduce?
Yeah. a private version. But it does the same, yeah.
Yeah, so I tried, for example, using the
maybe not actually.
the vector representation of x, which was 0, 1, 0. So is it expected not to so the factorization I get is like x2 and then 0, 1, 0, which is equal to x anyway, but in a different representation.
I didn't understand what.
So for example, I have x, and then I do an NF alg2 basis.
Yeah.
And then I append
So
it to the u. So then it looks like two different elements because
No.
one is in two.
No, alg2 basis doesn't work. What should work is using alg2 basis on the first column and leaving the second one. That's. But that you have a function that does exactly that.
No, no.
5 minutes? Okay. I'll answer questions later. There could be some bugs, actually. I expect there are some bugs. I say that it used reduce. Maybe this one does, maybe it doesn't. So maybe the reduce is only used in the very high level function. Here you waste time for nothing. So it doesn't include the reduction. Scratch that. So next slide. So powering is trivial. We just multiply the exponents. Division is trivial. We just subtract the exponents. We can compute norms. It's just the norm of every guy in the first column. And we actually should get some factorization of the norm, but it's actually expanded. Okay. Final slide. You can actually use NF factor back on a factorization whose elements are themselves factorization. It keeps the factorization structure. It's not recursive. But of course, you can apply NF factor back once more. So the first one, if U and V are in compact form, the first one is guaranteed to be very inexpensive. The second one might be very expensive. Okay? This will not work. I want the trace of an element in factor representation. Trace is additive, not multiplicative. Fade. Something else. Here I'm mapping things to a residue field. I get some element in the residue field. This has an inertia degree 2, I guess. That's why we get a polynomial here. Here I'm initializing computation for this group, 5. And I'm just mapping V this time to this group. I get something that works. Of course, this is non-trivial because the function only assumes that V is globally coprime to the modulus. It doesn't assume that every single generator in the factorization is coprime to the modulus. So there is something non-trivial in there. Here, also. Okay, so yeah, I want to finish in time. So.